deep inside every black hole, our best physics says, there lies a point where matter becomes infinitely dense and space-time tears apart completely. But what if this mathematical nightmare is actually impossible? What if the universe has secret safeguards that prevent these reality-breaking singularities from ever forming? We're about to journey through quantum firewalls that might replace black hole hearts, explore cosmic bounces that could have birthed our universe, and discover why the most brilliant minds in physics are now questioning everything we thought we knew about the most extreme objects in existence. If you're ready to have your mind blown by the possibility that singularities are just mathematical ghosts, hit that like button and subscribe for more reality-bending physics. Prepare yourselves. We dive deep. Picture a calculator trying to divide by zero and simply displaying error. That's essentially what happens when physicists try to describe the center of a black hole using Einstein's equations. The math doesn't just get complicated or difficult to solve. It literally breaks. The equations start spitting out infinities like a broken vending machine dropping endless candy bars. Here's the problem that has haunted physics for nearly a century. When matter collapses under its own gravity, Einstein's general relativity predicts it will keep crushing inward without limit. The density climbs higher and higher. First, atoms get squeezed closer together. Then, electrons crash into protons. Then even neutrons can't withstand the pressure. But the crushing doesn't stop there. According to the math, matter continues collapsing until it reaches infinite density at a single point with zero volume. Physicists call this nightmare scenario a singularity. It's like trying to squeeze the entire population of New York City into a space smaller than the period at the end of this sentence. Then keep squeezing. The curvature of space-time around this point also becomes infinite. Imagine rolling a bowling ball on a trampoline, watching it create a dip in the fabric. Now imagine that dip becomes so steep it forms a bottomless pit that tears the trampoline completely apart. That's what a singularity supposedly does to the fabric of reality itself. At this point, time stops making sense. Distance becomes meaningless. Every physical law we've ever discovered simply gives up and returns mathematical nonsense. It's as if nature itself throws its hands up in defeat and declares, "I can't compute this anymore." The truly unsettling part? Our most trusted theories predict these mathematical monsters should be lurking at the heart of every black hole in the universe. That means millions of points where physics completely breaks down are scattered throughout space right now. Some black holes contain the crushed remains of stars 20 times more massive than our sun, all compressed into mathematical points smaller than a grain of sand. Even worse, cosmologists believe our entire universe emerged from a singularity during the Big Bang. According to this view, everything we see around us, from planets to galaxies to the very atoms in your body, somehow expanded from a point of infinite density and temperature. The math suggests that at the very beginning of time, physics was not just broken, but utterly meaningless. This creates what philosophers call a crisis of explanation. How can our most successful scientific theories predict their own destruction? How can mathematics that accurately describes everything from GPS satellites to gravitational waves suddenly produce answers that make no physical sense? It's like having a perfect map that guides you flawlessly through every city and countryside, only to discover that certain locations are marked with "Here be dragons," and math stops working here. But what if the dragons are just figments of mathematical imagination? What if the real universe has built-in safeguards that prevent these reality-breaking points from ever actually forming? Einstein never wanted his theory to predict the destruction of physics itself. When he first developed general relativity in 1915, the equations were supposed to describe how massive objects bend the fabric of space-time. Stars, planets, even light beams would follow curved paths through this warped cosmic geometry. It was elegant mathematics that turned gravity from a mysterious force into the natural motion of objects through curved space. But mathematics has a way of revealing truths that even its creators never anticipated. Within just a few years, other physicists began finding solutions to Einstein's equations that he found deeply disturbing. These solutions described scenarios where matter could collapse so completely that it would disappear from the universe entirely, leaving behind regions where space-time itself became infinitely curved. Einstein fought back against these predictions. He published papers attempting to prove that such extreme collapses could never actually happen in nature. He argued that quantum effects, or the rotation of stars, or some other physical mechanism, would always prevent total gravitational collapse. He believed the universe must have natural limits that would stop matter from crushing itself out of existence. The problem is that Einstein's own equations disagreed with him. General relativity contains no built-in stopping mechanism. Once enough matter gets concentrated in a small enough region, the mathematics demands that collapse will continue indefinitely. It's like trying to design a car with brakes, only to discover that your engineering equations predict the brakes will fail whenever you need them most. Here's what makes this situation so unsettling for physicists. General relativity has passed every experimental test we've thrown at it. The theory correctly predicted that massive objects would bend starlight, that time would run slower in strong gravitational fields, and that accelerating masses would create ripples in space-time itself. When scientists detected gravitational waves from colliding black holes in 2015, they found the signals matched Einstein's predictions with incredible precision. So, we have a theory that works perfectly for describing everything, from falling apples to orbiting planets to colliding galaxies. But this same theory also predicts that under extreme conditions, physics itself will break down completely. It's like having a car that runs flawlessly on every road except the ones where you need it most. The mathematical breakdown occurs because general relativity treats space-time as a smooth, continuous fabric that can be curved without limit. Picture stretching a rubber sheet and placing increasingly heavy objects on it. The sheet will bend more and more, but in Einstein's mathematics, there's nothing to prevent it from being stretched into an infinitely deep pit. This creates what physicists call a geodesic incompleteness. Imagine you're following a perfectly straight path through curved space-time, but suddenly your path just ends. Not because you hit a wall or boundary, but because the mathematics simply stops providing meaningful answers. Your journey through space and time reaches a point where the equations throw up their hands and declare, "We can't tell you what happens next." But perhaps the most brilliant mind of the 20th century was wrong about his own theory. Perhaps nature does have hidden safeguards that Einstein never discovered, mechanisms that kick in precisely when his equations start producing infinities. Perhaps we're about to discover what really happens when matter tries to collapse beyond all limits. Step across the event horizon of a black hole, and according to Einstein's math, you're already dead. Not immediately dead, mind you. You might have hours or even days left, depending on the black hole's size. But from the moment you cross that invisible boundary, your fate becomes mathematically sealed. No force in the universe can prevent you from eventually reaching the singularity at the center, where you'll be crushed into a point of infinite density. This grim prediction has haunted physics for decades. The event horizon acts like a one-way membrane in space-time. Light can enter but never escape. Matter can fall in but never climb back out. It's the ultimate point of no return, marking the boundary between the normal universe and a region where physics breaks down completely. But here's where the story gets interesting. What if crossing the event horizon doesn't actually doom you to encounter a singularity? What if something happens inside black holes that prevents the infinite crushing that Einstein's equations predict? Think of it like walking toward the edge of a cliff in thick fog. From a distance, it appears that anyone who steps over the edge will fall forever into an infinite abyss. But what if, hidden by the fog, there's actually solid ground just a few feet below the cliff edge? What if the seemingly endless fall is just an optical illusion created by limited visibility? Recent advances in quantum physics suggest that black hole interiors might contain similar hidden features. Instead of crushing matter into mathematical points, the extreme conditions inside might trigger quantum effects that halt the collapse before it reaches infinite density. The singularity might be like a mirage that disappears when you get close enough to examine it carefully. One possibility is that matter falling toward the center encounters what physicists call quantum pressure. Just as normal matter resists being compressed beyond a certain point, quantum effects might create an even stronger resistance that kicks in at incredibly high densities. Instead of collapsing to zero volume, matter might bounce back like an extremely rigid spring being compressed to its limit. Another intriguing idea suggests that the fabric of spacetime itself has a granular structure at the smallest scales. If space is made of discrete units rather than being perfectly smooth, then matter can only be compressed until it reaches the size of these fundamental space pixels. It's like trying to squeeze a beach ball into a container smaller than a single grain of sand. The ball simply can't fit into a space smaller than the basic building blocks of space itself. These quantum effects would completely change what happens inside black holes. Instead of a crushing singularity, you might find a bizarre quantum realm where normal concepts of time and space operate according to entirely different rules. Matter might exist in exotic states never seen anywhere else in the universe. Energy and information might swirl in patterns that our current physics can barely describe. The most mind-bending possibility is that black hole interiors might contain entire universes in their own right, with their own laws of physics and their own possibilities for complexity and structure. But to understand how this could work, we need to dive deeper into the quantum realm, where reality itself might be fundamentally different than we imagine. At the smallest scales of reality, matter refuses to be pinned down. Quantum mechanics tells us that particles don't have definite positions or velocities until we measure them. They exist in clouds of probability, spread out across space, like ghostly possibilities waiting to become real. An electron orbiting an atom isn't following a specific path like a planet around the sun. Instead, it exists as a fuzzy probability cloud that somehow occupies multiple locations simultaneously. This quantum fuzziness might be exactly what saves the universe from singularities. When matter gets compressed to extreme densities, quantum effects become increasingly dominant. The normal rules of classical physics start breaking down, replaced by the strange logic of quantum mechanics, where particles can tunnel through barriers and exist in multiple states at once. Think of trying to squeeze a handful of ping-pong balls into a shrinking box. At first, you can pack them closer together by reducing the empty space between them. But eventually, you reach a limit where the balls themselves start resisting further compression. They push back against the walls of the box with increasing force as you try to squeeze them smaller. Quantum particles behave similarly, but with an added twist. As they get compressed into smaller and smaller volumes, their quantum uncertainty actually increases their effective size. The more precisely you try to confine a particle's position, the more violent its quantum motion becomes. It's like trying to grab a slippery fish with increasingly tight hands. The harder you squeeze, the more frantically it struggles to escape. This creates what physicists call quantum pressure or degeneracy pressure. When matter reaches densities of about 10 to the 15th grams per cubic centimeter, quantum effects generate enormous outward pressure that can halt gravitational collapse. That's roughly the density of crushing every car on Earth into a space the size of a sugar cube. At such extreme densities, quantum mechanics essentially rebels against further compression. But even this quantum resistance might not be strong enough to stop the collapse of the most massive stars. When a star more than 20 times heavier than our Sun dies, its core contains so much matter that quantum pressure gets overwhelmed by gravity. The collapse continues beyond the point where normal quantum effects can stop it. However, this is where things get truly exotic. As matter approaches the density where singularities supposedly form, quantum mechanics might deploy its most powerful weapon, the breakdown of space and time themselves. At incredibly tiny scales called the Planck length, roughly 10 to the minus 35 meters, the smooth fabric of spacetime might dissolve into a seething foam of quantum fluctuations. Imagine zooming into what appears to be a calm lake surface. From far away, it looks perfectly smooth, but as you get closer, you start seeing ripples, then waves, then violent turbulence. At the quantum scale, spacetime might be similarly turbulent, with tiny bubbles of space and time constantly appearing and disappearing in a chaotic dance. This quantum foam might make it literally impossible for matter to collapse to a mathematical point. Instead of reaching infinite density, matter might encounter a fundamental graininess of reality itself. But there's an even more radical possibility lurking in the equations of quantum gravity. There might be a fundamental speed limit for collapse itself. We're familiar with the cosmic speed limit for motion. Nothing can travel faster than light through space, roughly 186,000 miles per second. This isn't just a technical limitation of our current technology. It's a fundamental feature of reality that even the most advanced alien civilization could never overcome. The universe simply doesn't allow faster than light travel. But what if there's a similar absolute limit for how densely matter can be packed together? What if the universe has a built-in density speed limit that prevents singularities from forming, just as surely as it prevents faster than light travel? This hypothetical limit is called the Planck density, named after German physicist Max Planck, who first discovered the quantum nature of energy. At this incredible density, roughly 10 to the 94th grams per cubic centimeter, the very concepts of space and time begin to break down. To put this in perspective, imagine compressing the entire mass of the Earth into a volume smaller than a proton. Then compress it a trillion times more. At Planck density, the wavelength of quantum fluctuations becomes comparable to the size of the region containing all that matter. It's like trying to fit ocean waves into a bathtub. The waves simply can't exist in such a confined space. Similarly, the quantum fluctuations that give rise to space and time itself might be unable to fit into such compressed regions. This creates what some physicists call the Planck wall, an absolute barrier that prevents matter from being compressed beyond a certain point. Just as you can't push a physical object through a solid wall, matter might be unable to collapse past this quantum density limit. Instead of forming a singularity, collapsing matter would slam into this invisible barrier and bounce back. The bounce wouldn't be gentle. When matter hits the Planck wall, it might rebound with incredible violence, creating an explosion that could birth entire universes. Some cosmologists believe this is exactly what happened during the Big Bang. Instead of emerging from a singular point of infinite density, our universe might have been born from the violent rebound of matter that had collapsed in a previous cosmic cycle. This opens up mind-bending possibilities for what lies inside black holes. Instead of crushing everything into mathematical points, black holes might contain incredibly dense but finite cores bouncing against the Planck wall. Matter and energy might be compressed to the absolute limits allowed by physics, creating exotic states of matter that exist nowhere else in the universe. These cores might be seething with quantum energy, constantly creating and destroying virtual particles at rates that would make nuclear reactions look sluggish by comparison. They might exist in a state of suspended animation, where time itself becomes so distorted that billions of years in the outside universe correspond to mere moments in the core. Even more intriguingly, the Planck wall might not be a permanent barrier. Quantum mechanics allows for the possibility of tunneling, where particles can sometimes pass through barriers that should be impossible to cross according to classical physics. What happens when matter pressed against the Planck wall begins to tunnel through to the other side remains one of the deepest mysteries in theoretical physics. Space itself might be made of incredibly tiny building blocks. For over a century, physicists have assumed that space-time is smooth and continuous, like a perfectly flat sheet of paper that can be curved and stretched without limit. Einstein's general relativity treats space as an infinitely divisible fabric, where you can always zoom in further and find smaller regions to examine. But what if this assumption is completely wrong? What if space, when examined at the smallest possible scales, reveals itself to be grainy and discrete, like a digital photograph? What if the smooth fabric of reality is actually woven from countless microscopic threads that cannot be divided any further? This revolutionary idea forms the foundation of loop quantum gravity, one of the leading theories attempting to merge Einstein's relativity with quantum mechanics. According to this approach, space is constructed from fundamental units called loops that exist at the Planck scale. These loops are incredibly tiny, roughly 10 to the minus 35 meters across. To put this in perspective, a Planck-length loop is smaller compared to a proton than a proton is compared to the entire solar system. Think of zooming in to what appears to be a smooth photograph on your computer screen. From a distance, the image looks perfectly continuous, but as you zoom in further and further, you eventually start seeing individual pixels. Zoom in even more, and the smooth curves and gradual color changes resolve into a grid of discrete squares, each with its own specific color value. Loop quantum gravity suggests that space works similarly. The smooth geometry we observe at large scales emerges from the interaction of countless quantum loops at the smallest scales. Just as digital images are built from pixels, the fabric of reality might be constructed from these fundamental spatial atoms. This pixel-like structure of space creates a natural stopping point for gravitational collapse. Matter can only be compressed until it reaches the size of a single spatial pixel. Try to squeeze it smaller, and you're essentially asking space itself to occupy less than 1 unit of space, which is mathematically impossible. It's like trying to fit a digital photograph into fewer pixels than the image contains. When collapsing matter hits this fundamental limit, something remarkable happens. Instead of forming a singularity, the matter bounces back with tremendous force. The quantum geometry of space itself provides the resistance, like a trampoline, that can only be stretched so far before it snaps back. This quantum bounce prevents infinite density from ever forming. The calculations suggest that this bounce occurs when matter reaches a density of roughly 1/10 the Planck density. At this point, the repulsive quantum force becomes stronger than gravity itself, halting the collapse and reversing it into an explosive expansion. The collapsing matter doesn't disappear into a mathematical point. Instead, it rebounds like a superball, hitting a concrete wall. This has profound implications for black holes. Instead of containing singularities, they might house incredibly dense but finite cores that are constantly bouncing against the fundamental limits of space itself. But even more exotic possibilities emerge when we consider what happens to these quantum loops under extreme conditions. What if every particle in the universe is actually a vibrating string? This isn't just poetic language or philosophical speculation. String theory, one of physics' most ambitious attempts to describe reality at its deepest level, proposes that all fundamental particles are actually tiny one-dimensional strings vibrating in multiple dimensions. An electron isn't a point particle, but rather a string vibrating in one particular pattern. A photon is the same string vibrating in a different way. These strings are unimaginably small, operating at the Planck scale, where our normal concepts of size and distance begin to break down. But despite their tiny dimensions, they might hold the key to preventing singularities from forming anywhere in the universe. The crucial insight comes from how strings behave under extreme compression. Unlike point particles, which can theoretically be squeezed into infinitely small spaces, strings have a natural size limit. You can compress a vibrating guitar string to a certain point, but you can't make it smaller than the wavelength of its fundamental vibration. Push beyond this limit, and the string snaps back with tremendous force. Cosmic strings in string theory work similarly, but with a quantum twist. As matter collapses toward what would normally become a singularity, the fundamental strings that make up that matter begin vibrating more and more violently. The increased energy of vibration creates what physicists call stringy effects that generate enormous outward pressure. Think of blowing air into a balloon. At first, the balloon expands smoothly as you add more air, but there comes a critical point where the rubber can't stretch any further. Add even a tiny bit more air, and the balloon explodes with surprising violence. String theory suggests that collapsing matter behaves like an overstretched balloon, reaching a critical density where stringy effects cause it to explode outward rather than collapse inward. This string-powered explosion doesn't destroy the matter. Instead, it transforms it into exotic forms that exist in higher dimensions. The matter that was about to form a singularity gets converted into vibrating strings that extend into spatial dimensions we can't normally perceive. From our three-dimensional perspective, the matter appears to vanish. But from the higher dimensional viewpoint of string theory, it's still there, just reorganized into a completely different form. This creates what string theorists call a stringy resolution of the singularity problem. Black holes wouldn't contain infinitely dense points, but rather incredibly energetic collections of vibrating strings, extending through multiple dimensions. These strings might be oscillating so rapidly that they create their own pocket universes, complete with their own laws of physics. The math suggests that these stringy black hole cores might be connected to other regions of spacetime through higher dimensional pathways. Matter falling into a black hole might not be destroyed, but rather transported to distant parts of our universe, or even to entirely different universes altogether. But string theory isn't the only framework suggesting that black holes might be more exotic than we ever imagined. Recent discoveries about information and quantum mechanics are revealing even stranger possibilities for what might replace the dreaded singularity. Information, it turns out, might be indestructible in our universe. This isn't just about computer files or library books. In physics, information refers to the complete quantum description of any system, whether it's a single particle, a complex molecule, or an entire star. Quantum mechanics tells us that this information can never be created or destroyed, only transformed from one form to another. It's like a cosmic conservation law as fundamental as the conservation of energy. But black holes seem to violate this sacred principle. When matter falls past the event horizon, all the quantum information it carries appears to vanish forever into the singularity. From the outside universe's perspective, that information has been permanently erased from reality. This creates what physicists call the information paradox, one of the deepest puzzles in modern physics. The paradox becomes even more troubling when you consider Hawking radiation. Stephen Hawking showed that black holes slowly evaporate by emitting random thermal radiation. Over enormous timescales, even the largest black holes will completely disappear, leaving behind only this apparently random energy. If the original information that fell into the black hole isn't somehow encoded in this radiation, then it's been permanently destroyed. However, recent breakthrough research suggests that the information paradox might actually prove that singularities don't exist. If information truly cannot be destroyed, then black holes must have some mechanism for preserving and eventually returning all the quantum data that falls into them. But this would be impossible if that information were crushed into a singularity where physics breaks down completely. Think of it like burning a book in a fireplace. The physical book is destroyed, but all the information it contained is actually preserved in the exact arrangement of smoke particles, ash molecules, and heat radiation produced by the fire. The information becomes incredibly difficult to read, but it's still there in principle. A sufficiently advanced civilization with perfect measurement tools could theoretically reconstruct the original book by analyzing every particle produced by the burning. Black holes might work similarly. Instead of destroying information at a singularity, they might encode it in incredibly subtle patterns that get imprinted on the outgoing Hawking radiation. This would require the black hole's interior to maintain perfect quantum coherence, preserving every bit of information until it can be slowly released through radiation. But maintaining such perfect coherence would be impossible if the information ever reached a true singularity. The mathematical breakdown of physics at infinite density would scramble and destroy quantum information just as surely as throwing a computer into a furnace destroys the data on its hard drive. This suggests that black holes must have some kind of information, storage, and processing system that prevents singularities from forming. The interior might contain exotic quantum structures that preserve information while preventing infinite density. Matter falling in might be converted into pure information patterns that exist in a quantum realm where normal concepts of space and time don't apply. Some physicists now believe that understanding how black holes preserve information will lead us to discover the true quantum structure of gravity, and that discovery might reveal the most shocking truth about black holes yet. The center of a black hole might be the hottest, most energetic place in the entire universe. This contradicts everything we think we know about these cosmic monsters. Black holes are supposed to be the ultimate cold, dark objects where even light cannot escape. Their surfaces emit Hawking radiation at temperatures colder than the cosmic background radiation, making them literally the chilliest objects in space. From the outside, they appear as perfect spheres of absolute blackness. But if singularities don't exist, then something else must be lurking at the center of every black hole. And the leading candidates are all blazing with unimaginable energy. One possibility is that black hole cores contain what physicists call quantum firewalls. These aren't walls made of flame, but rather barriers of pure energy that exist at the boundary between normal spacetime and the exotic quantum realm inside. When matter approaches this firewall, it gets incinerated by temperatures that make the core of the sun look like an ice cube. These quantum firewalls might burn at temperatures of 10 to the 32nd power Kelvin. To put this in perspective, the center of the sun reaches about 15 million Kelvin. The quantum firewall would be roughly 10,000 trillion times hotter. At such temperatures, not only would atoms be completely vaporized, but even individual protons and neutrons would be torn apart into their constituent quarks. But the firewall might be just the beginning. Inside this blazing barrier, matter might be converted into pure quantum energy, existing in states that have no equivalent anywhere else in the universe. The crushed remnants of stars might become seething plasma of quantum fields, fluctuating billions of times per second. Another possibility is that black hole centers contain gravastars, gravitational vacuum stars, that are essentially bubbles of dark energy surrounded by ultra-dense shells. The interior of a gravastar would be filled with repulsive dark energy, pushing outward with incredible force, while the shell provides just enough gravitational pull to maintain equilibrium. The energy density inside such objects might rival what existed during the first moments after the Big Bang. These exotic cores might be constantly creating and destroying matter through quantum processes that operate on timescales incomprehensible to normal physics. Virtual particles might pop into existence and annihilate each other trillions of times per second, creating a cosmic furnace that makes nuclear fusion look like a gentle campfire. The truly mind-bending possibility is that these energetic cores might be manufacturing space and time itself. As matter falls into the black hole, it might not be destroyed, but rather converted into the raw material from which new regions of space-time are continually created. The black hole might be like a cosmic factory, constantly producing pocket universes that bubble off into dimensions we cannot perceive. This would mean that every black hole in our universe is essentially a birth canal for new cosmic realms, each potentially containing its own laws of physics and its own possibilities for complexity and life. But there's an even more radical interpretation of what might be happening inside these mysterious objects. Our entire universe might have been born from the collapse of a single star in another cosmic realm. This idea completely reimagines the origin story that cosmologists have been telling for nearly a century. According to the standard Big Bang model, our universe began as a singularity of infinite density and temperature. All of space, time, matter, and energy emerged from this mathematical point roughly 13.8 billion years ago in an explosive expansion that continues today. But if singularities are impossible, then our universe couldn't have started from an infinitely dense point. Something else must have triggered the Big Bang, something that doesn't require physics to break down completely at the moment of creation. The most compelling alternative is called the Big Bounce. Instead of emerging from nothing, our universe might be the result of a previous universe that collapsed almost to the point of forming a singularity. But just before reaching infinite density, quantum effects kicked in and caused the collapsing matter to rebound with tremendous force. The bounce created what we observe as the Big Bang expansion. Picture a rubber ball being thrown at the ground. It compresses as it hits the surface, storing all its kinetic energy as potential energy in the compressed rubber. Then it springs back, converting that stored energy into rapid expansion that launches the ball high into the air. Our universe might have experienced a similar cosmic bounce, with quantum effects providing the springiness that prevented total collapse. This bouncing universe model eliminates the need for a beginning entirely. Time might extend infinitely into the past, with an endless series of expansions and contractions. Each cycle could last hundreds of billions of years, with universes expanding, evolving, eventually contracting back to near singularity densities, then bouncing into new Big Bangs. But here's where the connection to black holes becomes fascinating. If our universe was born from a quantum bounce, then the same process might be happening inside every black hole in our current cosmos. When matter collapses past the event horizon, it might not form a singularity, but rather trigger a bounce that creates an entirely new universe inside the black hole. From our perspective, the matter disappears forever into the black hole. But from the perspective of that matter, it becomes the seed for a completely new cosmic realm. The interior of the black hole might actually be an expanding universe in its own right, potentially growing to contain billions of galaxies, stars, and planets. This leads to the mind-melting possibility that our own universe exists inside a black hole that formed in some parent universe. The Big Bang might have been the moment when matter in that parent cosmos collapsed to the quantum bounce point, creating our expanding spacetime as a kind of cosmic offspring. If this is true, then black holes aren't cosmic vacuum cleaners that destroy everything they touch. They're more like cosmic reproduction organs, constantly birthing new universes with their own independent existence. Every black hole in our sky might contain entire civilizations that evolved over billions of years in their own expanding spacetimes. But for this process to work, the universe must have built-in mechanisms that protect information and prevent true singularities from forming. The universe might be actively hiding its mathematical breakdowns from us. This isn't paranoia or conspiracy thinking. It's a serious scientific hypothesis proposed by some of the most respected names in theoretical physics. The idea is that nature has a built-in modesty that prevents us from witnessing the complete breakdown of physical laws. Whenever conditions arise that would create a naked singularity visible to outside observers, some mechanism kicks in to shield us from seeing it. Physicists call this the cosmic censorship hypothesis, and it's one of the strangest proposals in modern physics. According to this idea, singularities might exist, but they're always hidden behind event horizons, where we can never observe them directly. The universe essentially draws a black curtain around any region where physics stops making sense. Think of it like a cosmic witness protection program. Whenever mathematical monsters threaten to appear in public, nature quickly wraps them in event horizons that prevent anyone from seeing the breakdown of causality and physical law. From the outside, we see a perfectly normal black hole, but hidden inside, completely cut off from our ability to observe, physics might be having a complete nervous breakdown. But here's where the hypothesis gets really interesting. What if cosmic censorship works so well that it actually prevents singularities from forming in the first place? What if the mechanisms that hide breakdowns from our view are the same mechanisms that prevent those breakdowns from occurring? One possibility is that the very act of forming an event horizon creates quantum effects that halt the collapse before it reaches infinite density. The event horizon might not just hide the singularity from outside observers, it might prevent the singularity from forming by changing the quantum environment inside the black hole. When matter crosses the event horizon, it enters a region where the normal flow of time becomes severely distorted. From the outside perspective, anything falling into a black hole appears to slow down and freeze at the horizon, its image growing dimmer and redder until it fades from view. But this time, dilation might do more than just create visual effects. The extreme time dilation near the event horizon might give quantum effects unlimited time to build up and interfere with the collapse. Processes that would take infinitesimal fractions of a second in normal space might have billions of years to operate inside the distorted timescape near a black hole's center. Quantum fluctuations that would be negligible under normal conditions might accumulate into forces powerful enough to halt gravitational collapse. This creates a kind of quantum feedback loop. The stronger the gravitational field becomes, the more severely it distorts time. The more time gets distorted, the more time quantum effects have to build up resistance to further collapse. Eventually, this quantum resistance might become strong enough to prevent singularity formation entirely. The universe might be protecting us from mathematical monsters, not by hiding them, but by preventing them from existing in the first place. Cosmic censorship might work by ensuring that the conditions necessary for singularities to form are automatically self-correcting. But even if the universe has these built-in safeguards, recent discoveries about the quantum nature of black holes are revealing even stranger possibilities. You might be incinerated the moment you cross a black hole's event horizon. For decades, physicists believed that crossing the event horizon of a large black hole would be relatively peaceful. According to Einstein's equivalence principle, falling freely in a gravitational field should feel no different from floating in empty space. You might not even realize you've crossed the point of no return until you start feeling the tidal forces that would eventually stretch you into spaghetti. But in 2012, a group of physicists, led by Ahmed Almheri, dropped a bombshell that has divided the physics community ever since. They argued that the event horizon might not be the smooth, invisible boundary we've always imagined. Instead, it might be surrounded by a wall of incredibly high-energy radiation that would instantly vaporize anything trying to cross it. This firewall hypothesis emerges from attempts to resolve the information paradox we discussed earlier. If black holes must preserve all the quantum information that falls into them, then the outgoing Hawking radiation must be quantum entangled with the matter inside the black hole. But quantum mechanics forbids a single particle from being entangled with two different systems simultaneously. The math reveals a stark choice. Either the Hawking radiation is entangled with the black hole's interior, which preserves information but creates a firewall at the horizon, or the radiation is not entangled, which allows smooth passage through the horizon but destroys information forever. There's no middle ground that satisfies both requirements. Think of it like trying to have a phone conversation with two people simultaneously on a single phone line. The laws of physics say this is impossible. Either you're connected to one person or the other, but not both. Similarly, Hawking radiation particles can either be connected to the black hole's interior or to previously emitted radiation, but not to both. If the firewall exists, it would be unlike anything else in the universe. The energy density at the event horizon might approach the Planck scale, creating temperatures hot enough to instantly convert any form of matter into pure energy. Falling into a black hole wouldn't be a gentle journey toward a crushing singularity. It would be immediate annihilation in a furnace of quantum fire. But here's the twist that brings us back to the question of singularities. If firewalls exist, they might actually prevent matter from ever reaching the black hole's center. Instead of forming a singularity, All the material that falls into the black hole gets burned up at the horizon and converted into outgoing radiation. This would mean that black holes never actually contain any matter at all. They would be empty regions of curved spacetime surrounded by firewalls that convert infalling matter into radiation. The interior of a black hole might be completely hollow, with no singularity because there's no matter left to collapse. However, this solution to the singularity problem comes at a steep price. It would mean that black holes are not the cosmic recycling centers we thought, but rather the most efficient incinerators in the universe. Yet an even more radical possibility suggests that the very concept of a black hole interior might be an illusion. Everything that falls into a black hole might actually be stuck on its surface forever. This isn't some science fiction fantasy. It's one of the most profound insights to emerge from theoretical physics in the past 30 years. The holographic principle suggests that all the information about a black hole's interior is actually encoded in quantum fluctuations on the two-dimensional surface of the event horizon. Think about the hologram on a credit card. Despite appearing three-dimensional when you tilt it in the light, all the information creating that illusion is actually stored in a flat, two-dimensional surface. The holographic principle proposes that black holes work similarly. What appears to be a three-dimensional interior with matter falling toward a central singularity might actually be a projection created by information patterns on the black hole's surface. From the perspective of an outside observer, matter never actually crosses the event horizon. Instead, it gets smeared out across the surface, creating an incredibly thin layer of information that encodes everything about the infalling object. The object's mass, spin, electric charge, and every quantum detail get preserved as patterns in the quantum foam at the horizon. But here's where it gets mind-bending. If you're the one falling into the black hole, you experience crossing the horizon and continuing toward the center, exactly as Einstein's theory predicts. From your perspective, the interior is perfectly real and three-dimensional. You don't notice anything unusual about passing through the event horizon, and you definitely don't feel yourself getting flattened into a two-dimensional surface pattern. Both perspectives are equally valid according to the mathematics. The holographic principle doesn't say that one viewpoint is correct and the other is wrong. Instead, it suggests that these seemingly contradictory descriptions are actually two different ways of describing the same physical reality. This creates a remarkable solution to the singularity problem. If all matter is actually encoded on the black hole's surface rather than falling to the center, then there's no matter available to form a singularity. The center of the black hole might be completely empty, or it might not exist as a physical location at all. The three-dimensional interior that infalling observers experience would be a kind of holographic projection, as real to them as a vivid dream is to the dreamer, but ultimately constructed from information stored elsewhere. The singularity at the center would be like the vanishing point in a perspective drawing. It appears to exist from certain viewpoints, but it's actually just a mathematical artifact created by the way we choose to describe the geometry. This holographic description also elegantly resolves the information paradox. Since information never actually falls past the event horizon but instead gets encoded on the surface, it remains accessible to the outside universe. As the black hole evaporates through Hawking radiation, this surface information gets gradually released back into space. Nothing is lost. Nothing disappears into mathematical oblivion. But if the holographic principle is correct, it raises even deeper questions about the nature of space, time, and reality itself. The next chapters of our journey will explore these implications and reveal how the quest to understand black holes is leading us toward a completely new understanding of what the universe actually is. Black holes might be giant tangles of vibrating strings with no interior at all. Imagine trying to peek inside a ball of yarn that's been wound so tightly that its surface appears perfectly smooth from any distance. You might assume there's empty space in the center, but when you finally manage to look closer, you discover that the entire volume is filled with intricately woven threads. There's no hollow interior, just layer upon layer of incredibly fine filaments twisted together in patterns too complex to unravel. According to string theory's fuzzball model, black holes work exactly like this cosmic ball of yarn. What we perceive as empty space inside the event horizon is actually packed solid with quantum strings vibrating in 11-dimensional spacetime. These strings are wound and tangled so densely that they create the illusion of a smooth, spherical surface when viewed from our limited 3-dimensional perspective. The mathematics behind this idea are staggering in their implications. Instead of matter collapsing to form a singularity, it gets converted into incredibly long, thin strings that stretch and vibrate throughout the entire volume inside the event horizon. A single proton falling into the black hole might become a string millions of miles long, wound back and forth through higher dimensions like thread on a cosmic spool. These strings carry all the quantum information about the original matter, but encoded in their vibration patterns rather than in familiar forms of mass and energy. The pitch and rhythm of each string's vibration corresponds to specific properties of the particles that created it. It's like having a cosmic orchestra where every instrument represents a different piece of matter that fell into the black hole, and the symphony they play together encodes the complete history of everything the black hole has ever consumed. The fuzzball model completely eliminates the need for a singularity. There's no point at the center where density becomes infinite, because there is no center. The entire interior volume is occupied by these vibrating strings, creating a kind of quantum fabric that extends all the way out to the event horizon. Matter doesn't fall toward a central point of destruction. Instead, it gets absorbed into this cosmic tapestry, adding new threads to an already impossibly complex weave. From the outside, this string-filled interior would still appear to be a normal black hole. The event horizon would look the same. Hawking radiation would still be emitted at the expected rate, and the gravitational effects on nearby objects would be identical to what Einstein's theory predicts. But inside, instead of empty space leading to a singularity, there would be a seething mass of quantum strings vibrating in dimensions we can't directly perceive. This has profound implications for what happens to information that falls into black holes. Instead of being destroyed at a singularity, information gets woven into the string patterns inside the fuzzball. When the black hole eventually evaporates through Hawking radiation, this information gets gradually released back into the universe, encoded in the subtle quantum correlations between the emitted particles. But the fuzzball model raises an unsettling question about the very nature of the radiation that black holes emit. The energy bleeding from black holes might not be random evaporation, but rather active prevention of singularity formation. Stephen Hawking's most famous discovery seemed straightforward at first. Black holes emit radiation due to quantum effects near the event horizon, slowly shrinking over vast periods of time until they completely disappear. This radiation appeared to be a simple consequence of quantum mechanics operating in curved space-time, no more mysterious than steam rising from a hot cup of coffee. But what if Hawking radiation serves a much deeper purpose in the cosmic order? What if this energy leak is actually the universe's primary mechanism for preventing singularities from ever forming inside black holes? Consider what happens during the collapse that creates a black hole. As matter falls inward, it should eventually reach densities where quantum effects become dominant. At exactly this critical moment, the newly formed event horizon begins emitting Hawking radiation. The timing isn't coincidental. The radiation starts flowing outward, precisely when the interior matter is approaching the conditions that would create a singularity. Think of Hawking radiation like a pressure relief valve on a steam engine. As pressure builds inside the boiler, the valve automatically opens to release excess steam before the engine explodes. Similarly, as matter inside a black hole approaches infinite density, Hawking radiation might automatically increase to carry away the excess energy that would otherwise create a mathematical breakdown. Recent calculations suggest that this process is far more active than previously thought. Instead of being a passive byproduct of curved spacetime, Hawking radiation might be dynamically responding to conditions inside the black hole. When the interior matter starts approaching Planck density, the radiation rate could increase dramatically, siphoning away energy and preventing further collapse. This creates a kind of cosmic thermostat. The closer matter gets to forming a singularity, the more vigorously the black hole radiates energy away. The system automatically regulates itself to maintain a maximum density just below the point where physics would break down. It's like having a car that automatically slows down whenever you approach the speed limit, preventing you from ever actually exceeding it. But this regulatory mechanism operates on quantum timescales that are completely divorced from our normal experience of time. Near the center of a black hole, time dilation becomes so extreme that a single second of interior time might correspond to millions of years in the outside universe. The Hawking radiation has enormous amounts of time to build up and counteract the gravitational collapse. From the perspective of matter falling toward the center, this quantum regulation might manifest as an increasingly powerful outward pressure that builds up over what feels like eons of subjective time. What starts as a gentle resistance gradually becomes an overwhelming force that halts the collapse entirely. The matter never reaches infinite density because the universe gives quantum effects unlimited time to prevent it. This interpretation transforms black holes from cosmic destroyers into cosmic preservers. Instead of creating regions where physics breaks down, they become the universe's way of maintaining physical law, even under the most extreme conditions imaginable. However, some physicists propose that black holes might not even be holes at all. What if black holes are actually bubbles of dark energy masquerading as collapsed stars? This isn't just wild speculation. It's a serious theoretical proposal called the gravastar model, short for gravitational vacuum star. According to this idea, the objects we call black holes are actually hollow spheres filled with repulsive dark energy, surrounded by incredibly thin but ultra-dense shells of normal matter. Picture blowing a soap bubble, but instead of air inside, the bubble contains anti-gravity energy that pushes outward with tremendous force. The soap film represents a shell of matter compressed to nearly infinite density, while the dark energy interior pushes back with exactly the right amount of force to prevent the shell from collapsing inward or exploding outward. The result is a perfectly stable object that looks identical to a black hole from the outside. The gravastar model emerges from our growing understanding of dark energy, the mysterious force that's accelerating the expansion of our entire universe. This energy has a bizarre property. It creates repulsive gravity rather than attractive gravity. While normal matter pulls things together, dark energy pushes them apart. Most of the universe consists of this strange anti-gravitational substance, yet we barely understand what it is or how it works. But what if dark energy plays a crucial role in preventing singularities? When matter collapses under extreme gravitational pressure, it might trigger a phase transition that converts normal matter into dark energy. Instead of crushing down to infinite density, the collapsing material might flip into its opposite state, becoming a source of outward pressure rather than inward attraction. This phase transition would happen at densities just below the point where singularities would form. Think of water suddenly turning to steam when it reaches the boiling point. Similarly, normal matter might suddenly transform into dark energy when it approaches the density where physics would otherwise break down. The transition creates a hollow cavity filled with repulsive energy, surrounded by a thin shell of matter that never quite reaches infinite compression. From the outside, a gravastar would be virtually indistinguishable from a traditional black hole. It would have the same mass, the same gravitational effects on nearby objects, and even the same apparent event horizon. Light still couldn't escape from inside this boundary, not because space-time is infinitely curved, but because the dark energy interior creates such powerful, repulsive effects that photons get pushed back before they can reach the surface. The gravastar model elegantly solves several problems that plague traditional black hole physics. There's no singularity because the dark energy interior prevents infinite compression. There's no information paradox because information never disappears into a mathematical point. And there's no need for exotic quantum effects at the event horizon because the boundary isn't actually an event horizon in the traditional sense. Matter falling into a gravastar wouldn't be destroyed or crushed. Instead, it would add to the ultra-thin shell surrounding the dark energy core, gradually increasing the object's mass while maintaining its stable structure. The gravastar would grow larger, but remain fundamentally the same type of object. But this model raises profound questions about the nature of gravity itself under extreme conditions. Gravity might not be a fundamental force at all, but rather an illusion that emerges from deeper quantum processes. This idea challenges everything we think we know about the force that shapes the cosmos. For over 3 centuries, we've treated gravity as one of the basic forces of nature, as fundamental as electromagnetism or the nuclear forces that bind atoms together. But what if gravity is actually more like temperature or pressure, properties that emerge from the collective behavior of countless microscopic components? Think about the temperature of a gas. Individual molecules don't have temperature. They just move around with various speeds and directions. But when you have trillions of molecules bouncing around together, their collective motion creates what we experience as heat. Temperature isn't a fundamental property of matter. It's an emergent phenomenon that arises from underlying molecular chaos. Emergent gravity theories suggest that spacetime itself might work similarly. At the deepest level, reality might consist of quantum information bits that don't experience gravity at all. But when vast numbers of these information units interact together, they create the illusion of curved spacetime and gravitational attraction. What we call gravity would be a collective effect, like the temperature of a quantum gas. This has revolutionary implications for black holes and singularities. If gravity is emergent rather than fundamental, then it might simply stop working under extreme conditions. Just as the concept of temperature breaks down when you have only a few molecules, gravity might become meaningless when matter gets compressed beyond a certain threshold. Picture what happens when you zoom into a digital photograph far enough to see individual pixels. At normal viewing distances, the image looks smooth and continuous. But zoom in too far, and the illusion breaks down. You start seeing discrete chunks of color instead of flowing curves and gradual transitions. The smooth image is revealed to be an approximation that only works at larger scales. Emergent gravity suggests that space-time curvature works similarly. At normal densities and distances, Einstein's equations provide an excellent approximation of how matter and energy interact. But compress matter to extreme densities, and the smooth space-time description might break down entirely. Instead of infinite curvature and singularities, you might find that the very concept of curved spacetime becomes meaningless. This breakdown wouldn't be a catastrophic failure of physics. It would be more like reaching the resolution limit of a measuring instrument. When you try to measure something smaller than your ruler's finest markings, you don't get infinite measurements. You simply reach the limit of what that tool can tell you. Similarly, when matter reaches densities where emergent gravity breaks down, you wouldn't get infinite curvature. You'd reach the limit of what the gravity description can meaningfully describe. At this point, entirely different physics would take over. Instead of matter collapsing toward a singularity under gravitational attraction, it might be governed by whatever deeper quantum processes give rise to the gravity illusion in the first place. These fundamental interactions might have built-in limits that prevent infinite compression, naturally stopping the collapse before mathematical breakdowns occur. The challenge is figuring out what these deeper processes actually are and how they operate when gravity itself becomes an inadequate description of reality. Advanced mathematics might literally eliminate infinities from physics equations. This sounds like mathematical magic, but it's actually one of the most powerful techniques in modern theoretical physics. Renormalization allows physicists to take equations that produce infinite answers and systematically remove those infinities, leaving behind finite, meaningful results. It's like having a mathematical eraser that can delete the parts of equations that don't make physical sense. The technique was first developed to handle infinities that appeared in quantum field theory calculations. When physicists tried to compute the behavior of electrons and photons, their equations kept spitting out infinite answers for perfectly reasonable questions. Instead of giving up, they developed mathematical procedures to isolate these infinities and subtract them away, revealing the finite physical quantities hiding underneath. Think of it like cleaning a dirty window. The grime obscures your view, but underneath, there's perfectly clear glass. Renormalization procedures work similarly, removing the mathematical grime of infinities to reveal the clean physics beneath. The technique has been so successful that it forms the foundation of the standard model of particle physics, our most accurate description of the fundamental forces and particles. But here's where it gets interesting for black holes and singularities. What if the infinities that appear in Einstein's equations when matter collapses are just mathematical artifacts that can be removed through appropriate renormalization procedures? What if singularities are like computational bugs that can be fixed with better mathematical programming? Recent work in quantum gravity suggests that this might actually be possible. When quantum effects are properly included in the equations describing gravitational collapse, the infinities associated with singularities might cancel out through subtle mathematical relationships. The singularity wouldn't be prevented by physical forces. It would be eliminated by more accurate mathematics. This is analogous to what happened with the ultraviolet catastrophe in early quantum theory. Classical physics predicted that heated objects should emit infinite amounts of energy at short wavelengths, which obviously doesn't happen in reality. The resolution came not from discovering new forces, but from developing quantum mechanics, which naturally eliminates the problematic infinities through its built-in mathematical structure. Quantum gravity might work similarly for black hole singularities. The infinities in Einstein's equations might be artifacts of using classical descriptions for inherently quantum phenomena. When the proper quantum mathematics is developed, these infinities might disappear automatically, leaving behind finite descriptions of black hole interiors. The renormalized equations might predict that matter reaches a maximum density determined by quantum effects, then bounces back or transitions into exotic quantum states. Instead of crushing to infinite density, matter might undergo phase transitions, similar to how water turns to steam, but involving transformations between normal matter and pure quantum energy. This mathematical approach to eliminating singularities has the advantage of preserving most of our current understanding of physics while fixing its most troublesome predictions. General relativity would remain accurate for normal conditions, but its equations would be embedded within a larger quantum framework that automatically prevents mathematical breakdowns. However, testing these advanced theoretical ideas requires pushing physics experiments to previously unimaginable extremes. Scientists are creating artificial black holes in particle accelerators to test whether singularities can actually form. These aren't the stellar mass monsters we observe in space. Laboratory black holes would be microscopic entities lasting for incredibly brief moments before evaporating completely. But despite their tiny size and ephemeral existence, they might hold the key to understanding whether nature allows true singularities to exist. The experiments rely on smashing particles together at energies approaching the Planck scale, where quantum effects become dominant over gravitational ones. When protons collide at these incredible energies, they create conditions of matter and energy density that haven't existed since the first moments after the Big Bang. If singularities can form under any circumstances, these experiments should be able to create them. Think of it like stress testing a bridge by gradually adding more and more weight until something gives way. Engineers want to know the exact point where the structure fails and how it fails. Similarly, physicists are stress testing the fabric of space-time itself, pushing matter and energy to increasingly extreme densities to see if reality has a breaking point. The Large Hadron Collider in Europe has already created the highest energy densities ever achieved in controlled conditions. When lead nuclei collide at near light speed, they generate temperatures over 100,000 times hotter than the core of the Sun, and pressures that compress matter to densities rivaling neutron stars. Yet despite these extreme conditions, no singularities have been observed. Instead, the experiments have revealed something fascinating. At extreme densities, matter seems to undergo phase transitions that prevent infinite compression. Quarks and gluons, the building blocks of protons and neutrons, separate into a new state called quark-gluon plasma. This plasma behaves like a nearly perfect fluid, with properties that seem designed to resist further compression. Even more intriguingly, when this plasma expands and cools, it doesn't collapse back toward infinite density. Instead, it freezes into normal particles through a process that appears to have built-in safeguards against runaway compression. It's as if nature has multiple redundant systems in place to prevent matter from reaching the densities where singularities would form. Future experiments will push these boundaries even further. Next-generation particle accelerators might create conditions dense enough to probe the Planck scale directly, testing whether quantum gravity effects kick in to prevent singularities. These machines would be cosmic laboratories, recreating the conditions that existed inside the first black holes, or during the earliest moments of the universe. If laboratory experiments consistently fail to produce singularities despite reaching the necessary energy densities, it would provide powerful evidence that such mathematical monsters are indeed impossible in the real universe. The absence of laboratory singularities would suggest that astronomical black holes must contain something other than infinitely dense points at their centers. But the implications go far beyond black holes themselves. If matter has fundamental limits to how densely it can be compressed, those limits would apply everywhere in the universe, from the smallest subatomic scales to the largest cosmic structures. This brings us to a deeper question about whether all matter, not just the stuff inside black holes, might have absolute compression limits built into the laws of physics. Every type of matter in the universe might have an ultimate crushing point that cannot be exceeded. We already know this is true for certain kinds of stars. The Chandrasekhar limit tells us that white dwarf stars cannot exist if they contain more than about 1.4 times the mass of our Sun. Beyond this threshold, the quantum pressure supporting the white dwarf against gravity isn't strong enough to prevent further collapse. The star either explodes as a supernova or crushes down into something denser. Similarly, neutron stars have their own ultimate mass limit, called the Tolman-Oppenheimer-Volkoff limit. Pack more than about 3 solar masses worth of matter into a neutron star, and even the incredibly strong nuclear forces holding neutrons together can't resist gravity's pull. The star must collapse into something even more compact. But what if this pattern continues all the way down to the smallest scales? What if there's an ultimate limit for all matter, beyond which no physical force or quantum effect can prevent collapse? Paradoxically, this absolute limit might be exactly what prevents singularities from forming. Think of a series of increasingly strong safety nets stacked below a trapeze artist. The first net might be strong enough to catch a falling performer under normal circumstances. But if that net fails, there's a stronger one below it. And if that one fails, there's an even stronger net below that. Each successive safety net is designed to handle more extreme conditions than the last. Matter might work similarly. When gravitational pressure overwhelms the quantum forces supporting normal atoms, those atoms collapse into a neutron star. When gravity overwhelms the nuclear forces supporting neutrons, the matter might collapse into even more exotic forms like quark matter or strange matter. Each transition represents a new type of quantum resistance kicking in at higher densities. But the ultimate safety net might be space and time themselves. At the Planck density, roughly 10 to the 94th grams per cubic centimeter, the very concepts of space and time begin to break down. This isn't just another phase transition like the others. It represents a fundamental limit where the mathematical tools we use to describe compression simply stop making sense. Imagine trying to compress matter into a region smaller than space itself allows. It's like trying to fit a basketball into a container the size of a marble. The basketball doesn't compress to infinite density. It simply can't fit into the available space. Similarly, matter might be unable to compress beyond the fundamental granularity of spacetime itself. This creates what physicists call an asymptotic safety mechanism. No matter how much gravitational pressure builds up, there's always some quantum effect or spacetime limitation that provides just enough resistance to prevent singularity formation. The universe might have an infinite hierarchy of safety nets, each one stronger than the last, ensuring that matter can never quite reach the mathematical breaking point. Recent theoretical work suggests that this might indeed be how reality operates. Instead of a single, all-powerful force preventing singularities, there might be an endless cascade of increasingly exotic physics that kicks in whenever matter approaches its ultimate limits. But these safety mechanisms might connect black holes to the most exotic structures in spacetime itself. The center of every black hole might be a gateway to another region of spacetime. This isn't science fiction fantasy. It's a serious possibility that emerges naturally from Einstein's equations when you follow them to their logical conclusion without assuming that singularities must form. If matter can't collapse to infinite density, then the space-time geometry inside black holes might curve back on itself, creating tunnels that connect distant regions of the universe. Picture space-time as a vast sheet of rubber stretched tight. Normally, massive objects create dimples in this sheet, and smaller objects roll around following the curved paths created by these gravitational wells. But what if the most massive objects create dimples so deep that they punch completely through the sheet, creating holes that connect to other parts of the cosmic fabric? These spacetime tunnels are called Einstein-Rosen bridges, or more commonly, wormholes. The mathematics describing them has been around since the 1930s, but physicists have generally assumed they couldn't exist in the real universe because they would require exotic matter with negative energy density to remain stable. However, if singularities are impossible, then black holes might naturally evolve into wormhole-like structures without requiring any exotic matter at all. Here's how it might work. As matter falls toward what would traditionally become a singularity, quantum effects prevent infinite compression by creating an outward pressure that eventually overcomes gravity's inward pull. But instead of simply bouncing back, this quantum rebound might be so violent that it tears a hole in the fabric of spacetime itself. The tear wouldn't destroy spacetime, but rather connect it to another region, possibly in a distant part of our universe, or even in a completely separate cosmic domain. Matter falling into the black hole wouldn't be crushed out of existence. Instead, it would travel through this space-time tunnel and emerge somewhere else entirely. From the outside, this process would be completely invisible. The black hole would still appear to have an event horizon that prevents light from escaping. Observers watching objects fall in would still see them appear to freeze and fade at the horizon due to extreme gravitational time dilation, but the objects wouldn't actually be destroyed. They would be taking a shortcut through space-time to emerge at the other end of the wormhole. The other end of the tunnel might be a white hole, a theoretical object that spews matter and energy outward instead of sucking it in. While black holes are regions where nothing can escape, white holes would be regions where nothing can enter. Matter traveling through the wormhole would be forced to exit into normal space-time at the white hole location. This creates a cosmic recycling system where matter consumed by black holes gets transported to distant regions and expelled as white holes. Instead of being permanently removed from the universe, the matter would simply be relocated to different areas of space-time. Information wouldn't be destroyed because the matter carrying that information would continue to exist, just in a different location. But this exotic space-time plumbing might be just one manifestation of an even deeper principle governing how the universe protects itself from mathematical contradictions. The The universe might be fundamentally self-correcting, automatically preventing any scenario that would lead to logical contradictions. This principle, known as the bootstrap paradox or consistency principle, suggests that the laws of physics are designed to prevent their own violation. Just as a computer program with good error-checking routines will automatically fix or reject commands that would cause the system to crash, the universe might have built-in safeguards that prevent any situation from arising that would break the fundamental rules of reality. Think of it like a cosmic immune system. When your body encounters a virus or harmful bacteria, specialized cells automatically mobilize to eliminate the threat before it can cause serious damage. Similarly, when conditions arise that might lead to singularities or other mathematical breakdowns, the universe might automatically deploy quantum effects, space-time curvature limits, or other mechanisms to neutralize the threat to physical law. This isn't mystical thinking or anthropomorphic projection. It's a serious hypothesis about how quantum mechanics and general relativity might work together at the deepest level. The idea is that the universe has a kind of built-in intelligence, not in the sense of conscious thought, but in the sense of having self-regulating mechanisms that maintain consistency and prevent paradoxes. The bootstrap principle would explain why every mechanism we've discussed for preventing singularities seems to kick in at exactly the right moment and with exactly the right strength. Quantum pressure builds up just as matter approaches infinite density. Space-time granularity becomes important precisely when smooth geometry would break down. Hawking radiation intensifies exactly when black hole interiors reach critical conditions. It's as if the universe is constantly monitoring itself for potential problems and automatically deploying countermeasures whenever needed. The timing isn't coincidental. It's the result of deep principles that ensure physical law remains self-consistent under all possible circumstances. This bootstrap mechanism might explain not just the absence of singularities, but many other puzzling features of physics. Why do the fundamental constants of nature have exactly the values needed for stars, planets, and life to exist? Why do quantum mechanics and relativity mesh together so perfectly, despite being based on completely different mathematical frameworks? Why does information seem to be conserved even in the most extreme situations? The answer might be that the universe is actively self-selecting for consistency. Physical laws that would lead to contradictions or breakdowns simply can't exist in a self-consistent reality. The universe bootstraps itself into existence by requiring that all its component parts work together harmoniously. This creates a kind of cosmic natural selection where only self-consistent physical laws can survive and propagate. Laws that would create singularities, destroy information, or violate fundamental principles get automatically eliminated by the universe's built-in error correction mechanisms. The implications are staggering. If the universe is truly self-correcting, then every mystery in physics might have elegant solutions that preserve both mathematical consistency and physical intuition. The strange quantum effects that prevent singularities wouldn't be accidents or coincidences. They would be inevitable consequences of living in a reality that cannot tolerate self-contradiction. But to understand how this cosmic error correction operates, we need to examine the quantum foam that might underlie all of spacetime. At the smallest scales of reality, space and time might be constantly bubbling with virtual particles and spontaneous fluctuations. Imagine zooming into the surface of the ocean with an increasingly powerful microscope. From a distance, the water appears perfectly smooth and calm. But as you look closer, you start seeing ripples, then waves, then individual water molecules bouncing around in chaotic thermal motion. At the molecular level, what seemed like a stable, solid surface reveals itself to be a seething mass of constant activity. Physicists believe that spacetime itself works similarly. At the scale of everyday experience, space appears to be a smooth, continuous fabric that can be gently curved by massive objects. But zoom in to the Planck scale, roughly 10 to the minus 35 meters, and this smooth geometry might dissolve into a foam of quantum fluctuations, where the very concepts of distance and duration lose their meaning. This quantum foam consists of virtual particles constantly popping in and out of existence, borrowing energy from the vacuum and paying it back so quickly that the debt goes unnoticed by the universe's accounting system. Space itself might be made from these fleeting quantum events, like a movie screen made of pixels that flash on and off billions of times per second to create the illusion of smooth motion. At these scales, the normal rules of physics break down completely. Particles can tunnel through barriers that should be impenetrable. Energy can be borrowed from nothing and returned to nothing. Cause and effect become fuzzy concepts as quantum events happen faster than information can travel between them. It's a realm where logic itself becomes probabilistic rather than absolute. This quantum foam might be exactly what prevents singularities from forming inside black holes. When matter gets compressed to densities approaching the Planck scale, it encounters this seething quantum chaos, where the smooth space-time description that predicts singularities simply stops making sense. You can't compress matter into a region smaller than the quantum foam bubbles that make up space itself. Think of trying to squeeze a sponge into a space smaller than its individual pores. The sponge resists compression because its structure is made of discrete holes and connections. Similarly, matter might resist compression to sub-Planck densities because space-time itself is made of discrete quantum events that can't be squeezed any smaller. But the quantum foam might do more than just provide resistance to compression. It might actively intervene to prevent singularities through mechanisms we're only beginning to understand. Virtual particles near the Planck scale might interact with collapsing matter in ways that generate powerful outward forces. Quantum tunneling effects might allow matter to escape from regions where classical physics predicts it should be trapped forever. The foam might even allow matter to tunnel through the barriers that create event horizons, enabling information to escape from black holes through quantum processes that operate faster than light. This wouldn't violate relativity because the information wouldn't be traveling through normal space. It would be moving through the quantum substrate that underlies space itself. Understanding this quantum foundation of reality might be the key to resolving not just the singularity problem, but the deepest mysteries about measurement and observation in quantum mechanics. Observing a singularity might be fundamentally impossible according to the laws of quantum mechanics. This isn't just a practical limitation of our current technology. It might be a deep principle of physics that makes singularities literally unobservable, even in principle. If something cannot be observed under any circumstances, then quantum mechanics suggests it might not exist in any meaningful sense. The problem starts with the basic rules of quantum measurement. In quantum mechanics, the act of observation changes the system being observed. This isn't because our measuring instruments are clumsy or invasive. It's a fundamental feature of reality at the quantum scale. The universe exists in quantum superposition until the moment of measurement, at which point it chooses a specific outcome from all the possibilities. But what happens when you try to observe something that would require infinite measurement precision? A true singularity would have infinite density, infinite curvature, and occupy zero volume. Measuring any of these properties with perfect accuracy would require instruments with infinite precision, infinite energy, and zero size. Quantum mechanics tells us that such measurements are not just practically impossible, but theoretically meaningless. Think of trying to measure the exact position of a quantum particle. The more precisely you try to pin down its location, the more uncertain its momentum becomes. This isn't a limitation of measurement technology. It's a fundamental trade-off built into the structure of reality. Similarly, the more precisely you try to measure the properties of a forming singularity, the more the quantum uncertainty principle interferes with your ability to determine whether a singularity has actually formed. The uncertainty principle might create a kind of quantum censorship, that prevents us from ever witnessing the moment when matter reaches infinite density. As the density approaches infinity, the quantum uncertainty in that measurement also approaches infinity. At the exact moment a singularity would form, our ability to measure whether it has formed becomes completely undefined. This creates a bizarre situation where singularities might be forever hidden behind a veil of quantum uncertainty, rather than being hidden behind event horizons. Even if you could somehow survive falling into a black hole and traveling to its center, the quantum measurement problem might prevent you from ever determining whether you've encountered a true singularity or just an extremely dense but finite concentration of matter. The measurement problem becomes even more interesting when you consider that quantum mechanics is fundamentally about information. Every quantum system can be described in terms of the information it contains and the information it can provide when measured. But a singularity would contain infinite information compressed into zero volume, creating an information density that breaks the mathematical framework of quantum mechanics itself. This suggests that singularities might be quantum mechanically forbidden, not because of forces or energy considerations, but because they would create information paradoxes that violate the basic structure of quantum theory. The universe might prevent singularities from forming simply because allowing them to exist would make quantum measurement impossible. If this interpretation is correct, then the question of whether singularities exist might be answered not by better telescopes or more powerful computers, but by deeper understanding of how measurement and reality are connected at the quantum level. Within the next few decades, we might have instruments sensitive enough to directly test whether singularities exist inside black holes. This technological revolution won't come from building bigger telescopes or more powerful particle accelerators. Instead, it will emerge from our growing ability to detect and manipulate individual quantum particles with perfect precision. These quantum sensors might be sensitive enough to probe the information content of Hawking radiation and determine whether it carries traces of singularity formation. The key insight is that if singularities don't exist, then the Hawking radiation emitted by black holes should contain subtle patterns that reflect the exotic quantum processes happening inside. Each photon in this radiation would carry a tiny piece of information about the black hole's interior structure. Advanced quantum detectors might be able to read this information like a cosmic message encrypted in starlight. Think of it like forensic analysis of incredibly faint evidence. Crime scene investigators can sometimes reconstruct entire events from microscopic traces of DNA, fingerprints, or chemical residues. Similarly, quantum forensics might allow us to reconstruct what's happening inside black holes by analyzing the quantum correlations between individual particles in the outgoing radiation. The technology would rely on quantum entanglement detectors that can measure correlations between particles separated by vast distances. If black hole interiors contain quantum firewalls, fuzzballs, or other exotic structures instead of singularities, these alternative configurations should create specific correlation patterns in the emitted radiation. Different models of black hole interiors would produce different quantum fingerprints that advanced detectors could distinguish. Space-based gravitational wave observatories might provide another avenue for testing singularity theories. When black holes merge, they create ripples in space-time that carry information about their internal structure. If the merging objects contain exotic quantum cores instead of singularities, the gravitational wave signatures should differ subtly but detectably from what Einstein's classical theory predicts. Future quantum computers might also play a crucial role by simulating black hole formation with unprecedented accuracy. These machines could model the quantum effects that prevent singularity formation, allowing physicists to make precise predictions about observable signatures that current computers are too limited to calculate. But perhaps the most exciting possibility involves laboratory creation of artificial black holes using advanced particle accelerators. Next-generation machines might create microscopic black holes that exist long enough for their internal structure to be studied directly. If these laboratory black holes consistently fail to develop singularities despite reaching the necessary density thresholds, it would provide definitive proof that such mathematical monsters are impossible in nature. The timeline for these breakthroughs is surprisingly short. Quantum correlation detectors sensitive enough to analyze Hawking radiation might be available within 20 years. Space-based gravitational wave observatories could be operational within 30 years. Quantum computers capable of simulating black hole physics might emerge within 40 years. Within a single human lifetime, we might definitively answer whether the most extreme objects in the universe contain mathematical infinities or exotic but finite quantum structures. The age of speculation about black hole interiors could give way to an era of direct experimental verification. But whatever we discover will likely force us to completely reimagine our understanding of space, time, and the fundamental nature of reality itself. If singularities don't exist, we're on the verge of the greatest revolution in physics since quantum mechanics was discovered. The implications extend far beyond black holes themselves. Every area of theoretical physics, from cosmology to particle physics to quantum gravity, would need to be reconsidered in light of this fundamental discovery. We would be living through a scientific transformation comparable to the shift from Newton's clockwork universe to Einstein's relativistic cosmos. Consider what it would mean for our understanding of the Big Bang. If singularities are impossible, then our universe couldn't have emerged from a point of infinite density. The standard cosmological model would need to be replaced with bounce scenarios, eternal inflation theories, or completely new frameworks that we haven't even imagined yet. The very concept of a beginning to time might be abandoned in favor of cyclical or eternal models. Particle physics would face equally dramatic changes. The mathematical techniques that physicists use to calculate particle interactions often involve integrating over infinite ranges and removing infinities through renormalization procedures. If nature truly abhors infinities, then these mathematical methods might be telling us something deep about the structure of reality itself. Physical theories that naturally avoid infinities might be pointing toward more fundamental descriptions of matter and energy. The revolution would also transform our understanding of information and computation. If black holes preserve information through exotic quantum processes rather than destroying it in singularities, then the universe operates like a vast quantum computer that never loses data. This could lead to new insights about consciousness, artificial intelligence, and the relationship between physical processes and information processing. But perhaps the most profound change would be philosophical. For centuries, physicists have accepted that their theories might break down under extreme conditions. Singularities represented the ultimate breakdown, points where mathematics itself gives up and admits defeat. If these mathematical monsters don't exist, it suggests that the universe is more elegant and self-consistent than we ever dared hope. This could usher in an era of beautiful physics, where mathematical elegance and physical intuition work together harmoniously. Instead of accepting ugly infinities and arbitrary parameters, physicists might discover that reality operates according to principles of mathematical beauty and logical consistency that make exceptions impossible. The technology emerging from this revolution could be transformative. Understanding how quantum effects prevent singularities might teach us to manipulate spacetime itself, leading to advances in transportation, communication, and energy production that would seem magical by today's standards. If black holes are cosmic recycling centers rather than cosmic destroyers, we might learn to harness their exotic physics for purposes we can barely imagine. The search for a theory of everything would take on new urgency and new hope. Instead of trying to unify theories that break down under extreme conditions, physicists would be seeking a single mathematical framework that remains beautiful and consistent under all possible circumstances. Such a theory might finally reveal why the universe exists at all, and why it operates according to the specific laws we observe. We stand at the threshold of answering one of the deepest questions ever asked. Does mathematics describe reality, or does reality transcend mathematics? The answer might reshape not just physics, but our entire understanding of existence itself.